priors about the world that come from the data, and also arguably greater success from using these later approaches compared to the earlier approaches. So then I guess perhaps one kind of natural conclusion from this is that we should actually try to use even more data-driven priors compared to these approaches and try to explicitly learn priors from previous experience in a way that is optimized for efficient downstream learning. And I think this is one way of thinking about the meta-learning process. Can we explicitly learn how to learn so that when we try to learn something new, we can be efficient or can have other properties that we want from our learning processes? So what can this kind of few-shot meta-learning enable? I'll show a few examples here. So in some of our prior work, we showed how you can take previous experience with lots of different objects and then use that to, given a human video for a new object, be able to learn how to place that new object into a new bowl with only a single video of a human. Outside of robotic manipulation, we've also seen examples in predicting the properties of different molecules with a small amount of data from that molecule, using meta-learning and using previous experience from other molecules and other data. In the domain of legged robots, we've also looked at adapting from previous experience in simulation so that you need much less data in the real world. And you can adapt in just a few episodes to get a policy that can run further. And as another example of a diverse application, we've also seen scenarios that try to adapt to new regions of the world by taking previous experience in other parts of the world. And I think that all of these are examples of taking previous experience and using that to more quickly learn something new. So that's, I guess, maybe a very brief overview of why I think meta-learning is quite interesting, an example of how broadly applicable these kinds of ideas are. Now, what I'd like to really focus on in this talk is how we might be able to actually deploy these algorithms into a real-world application. Essentially, on the previous slide, I showed some things that are pretty nice demos, but to actually deploy something in the real world, it is harder. And I'll talk about one particular real-world problem, which is the feedback problem that comes up in education, and how we might be able to approach the problem using meta-learning, whether we can deploy it to real students, and we'll look at a few different examples of this problem. And then I'll conclude by talking about kind of an outlook for future work on and what we learned from actually trying to deploy these algorithms in a real application. So I guess to set the stage, I guess first this was work done by some really amazing collaborators, spearheaded by Mike Wu, and it wouldn't have been possible with everyone on the team, especially Chris, who is an expert on the education side. And I should mention that at the outset of this project, Chris and I had some conversations. We talked a little bit with Mike, and we wanted to see if we can try to make some progress on problems in education. But we had no idea how hard the problem was going to be. And we didn't, I guess at the outset, we didn't really think that we would be able to actually get to the deployment stage. We thought that maybe we can show some gains over previous approaches, but really had no idea how far we would be able to get. And explicitly what the problem is in particular, I guess there's this code in place course that was taught in 2021. It's also going to be taught next year as well. And it's a free course on Intro to Computer Science. It has 12,000 students from more than 150 countries across the world. So here's a heat map of where some of those students come from. And the students take a diagnostic during the course. And the first time Code in Place was offered, the students took a diagnostic and they didn't get any feedback on it. It was just kind of an exercise. And the reason why they didn't get feedback was because there were so many students. It was so time consuming. And the submissions here are open-ended Python code snippets. And we estimated that it would take around 8 months of human labor to give feedback to all these students. Now, of course, this problem actually isn't unique to Code in Place. So if you look at other online courses that try to teach people how to code or try to teach people other things, these courses also don't give very good feedback. So if you look at actually explicitly what the feedback looks like in massive online courses, it's not very satisfying. So Code Academy, for example, will just essentially give you like syntax errors, the kind of errors that the compiler might give you. Code.org will try to give you feedback, but it will typically be of the form of telling you that you didn't get it correct and that you should try something different. even for fairly constrained programs. And lastly, Coursera, again, doesn't really provide feedback. It just tells you whether or not you got the correct answer or not. And this isn't just, these platforms are really great. I'm not kind of intending to say anything negative about them. It's just to emphasize that this problem is very difficult and very real. Now, we can frame this problem of giving feedback as a classification problem. And in particular, you can define a rubric that has the set of kind of common misconceptions that students make, such as having incorrect syntax or not looping appropriately, or being correctly using a print function or not. And then the problem becomes taking a model that takes as input the student code and then outputs which misconceptions they made. And this sort of rubric-based approach is exactly what instructors use to give feedback in courses. This is like the kind of the standard, not just in university education, also in high school education and so forth. And so, and defining the rubrics isn't the hard part. The hard part is actually filling in all those rubrics. It's very time consuming for instructors to do. So we can frame the problem as a multi-label classification problem once we have a rubric defined. And then it becomes maybe a little bit more clear how we might apply machine learning to this problem, because we want to train a function that can take as input the student solution and predict the misconceptions, fill in the rubric for that solution. So why is this hard? It seems like once we formulate a classification problem, it should be possible to just kind of apply machine learning to the problem. However, there's a number of things that make this quite challenging for machine learning out of the box. The first is that there's very limited annotation. So grading student work is very time consuming. And as I mentioned before, it might require like lots of hours to collect a data set. The second is that the students will solve problems in many, many different ways. They'll have many different, they'll make mistakes in many different ways. And there's a number of work that show that a lot of the variation in student solutions often follows something like a power law. And then lastly, and perhaps most saliently, is that instructors will actually constantly change their assignments and exams. And so this means that the rubrics are going to look different from year to year, the problems are going to look different from year to year, and the student solutions will look very different each year. And so it makes it very difficult to collect a really massive data set and just apply machine learning on it directly. And then beyond machine learning, I should also mention that kind of crowdsourcing based approaches have also really struggled to solve the problem and have made it difficult to try to cover the solution, cover the kind of the space of problems or the space of solutions in the space of misconceptions. Okay, so from that standpoint, now this kind of brings up the question of whether meta learning and specifically few-shot meta learning might be able to help with this problem. And the reason why meta learning might be an effective approach is that we actually have a lot of previous experience. So we might have a lot of previous exam problems and homework problems that aren't exactly on the problem that we want to grade and give feedback on, but that are quite relevant to the target task. And what we envision is that we want to be able to leverage this previous experience such that the instructors can give feedback on a few student solutions and then have the system handle the rest. And so this is really a fairly classic few-shot learning problem. Now, what I'm going to do is I'm going to show you the results of what we did, and then I'll tell you a bit how it works. So on May 10th of last year, these students took the code in place diagnostic, and this resulted in 16,000 student solutions. We actually promised that we would give feedback on all of these solutions, I think within a week or so. And we designed a user interface to actually provide the feedback to the students. It's not just about actually filling in the rubric, but actually providing the kind of corresponding message that goes with those rubric items. And so the UI looks something like this. The feedback corresponding to the rubric item is shown in this purple box. The students would evaluate the feedback saying if they agree with it or not. And then we'd also kind of use attention to kind of highlight where the misconception might come from. And it's also worth mentioning that kind of in this particular program, for example, a syntax error right here would prevent any sort of unit testing approach to providing feedback from being useful. And these kinds of things come up all the time, making it very difficult to auto grade assignments. And so once we developed our meta learning system, we ran a blind randomized trial evaluated by the real students in the course. And in particular, we had kind of human volunteers give feedback on around 1,000 answers. And we used this to kind of seed the meta learning system. We also actually fine-tuned on these examples because we had enough of them. And then we had the system give feedback on the remaining 15,000 solutions. I should also mention that around 2,000 of the solutions could actually be auto-graded. And so we didn't include those examples in the analysis. And what we found after we deployed the system is that when we measured the agreement, like how often the students agreed with the feedback on the human solutions or the human feedback versus the feedback from the meta learning system, we actually found that humans gave very good feedback. They agreed with it around 96 to 97% of the time. And they actually agreed with the meta learning model slightly more, around 97 to 98%. Of course, agreement isn't everything. They might just agree with it because they think the feedback is great, or they are getting positive reinforcement or something like this. And so we also asked the students if they found the feedback useful. And on a score of 1 to 10, or 1 to 5, they kind of rated the usefulness of this feedback as a 4.6 out of 5. And so overall, we found this to be quite successful and definitely exceeded our expectations in terms of actually being able to use meta learning for this application. And also in the analysis, we also found that we weren't expecting this and any sort of bias, but it's good to double check these sorts of things. And we also didn't find any signs of bias by demographics. Cool. So those are like the key results. And so in the rest of this talk, I'll talk about how does the system actually work? Can we go further? And what are some of the outstanding challenges and directions for future work informed by these applications? So how does it work? So the meta training data set that we had corresponded to 4 final exams and 4 midterm exams from Stanford's Intro CS course, CS 106. And this has a total of 63 different questions and 24.8 thousand student solutions. And all the student solutions has feedback that's provided via a rubric. Like I mentioned before, this rubric-based grading is what is used to give feedback to students on exams and assignments. And 10% of the questions were also annotated by more than one TA, which allowed us to compute human accuracy on this particular data set in contrast to the live deployment. And so each rubric has several different items. Here's a few example rubrics on the bottom here. And each item has options that may be true or not true. For example, you could have a syntax error and a null pointer exception. And so you might have, some of these might be, more than one of these may be true. And so you can think of this as a kind of a multi-label binary classification problem. And then every problem has its own rubric item and options. And many of those rubric items and options are unique. Not all of them are. And so, for example, the perfect metric is something that comes up on a lot of rubrics, whereas other rubric options are more unique. Now, how do we actually frame this as a meta-learning problem? So what we're going to do is we're actually going to treat every rubric option, so all of those binary classification tasks, as a task that we're going to try to meta-learn across. And so this will then construct a total of 259 tasks because we're not just treating every rubric as a task, we're going to be treating every single option on those rubrics as a task. And so, for example, if we have a rubric right here, whether or not the solution is perfect or not is a task, whether or not the student incorrectly got a character to insert is also a task. If it incorrectly assumes 1 digit, that's yet another task, and so forth. So this gives us 259 tasks, and then we're going to essentially learn how to learn those tasks so that we can then very quickly learn to fill out new rubrics. To solve this problem, we're going to build upon the idea of prototypical networks, which, like a lot of few-shot meta-learning approaches, will separately form a support set and a query set for each rubric. And so each of these examples is going to be a different student solution and label for that rubric option. And we'll have I think in our experiments, we used 10 examples in the support set and 10 examples to use in the query set. And the support set will be used to derive a prototypical embedding for each label. And then we'll try to classify each example in the query data set, so all of the examples that are held out, by measuring the distance to the prototype and picking the prototype that is closest, picking the corresponding label. And so you can kind of view this as kind of visualized here, where we take the training data points for each of the two classes. Here, there'll just be two classes, and then compute this average embedding for each of the examples within that class, and then classify new data points by checking how close they are to each of the prototypes. You can formalize that with this equation here, where kind of P is the average embedding or the prototype for each of the two classes. Then we're going to compare the embedded test input to that prototype, measure the negative L2 norm, and then take the softmax of that to get a corresponding prediction. And then we also use the temperature here. Okay, and so that was kind of a very brief primer on prototypical networks. Because we're applying this to code, each of our examples is a sequence of discrete tokens. And so what we're going to do is for our model F, we're going to use a Roberta model or a stacked transformer, and then apply prototypical networks. So we basically just kind of combine this transformer model with prototypical networks and train it in the typical way. Now, unfortunately, if you just do this simple combination of these two things, it doesn't work. Out of the box, it doesn't give us very good performance, and we needed to apply several tricks to get past the fact that we didn't have that much meta training data. And so attention isn't quite all you need. So I'll go over just 3 tricks that that were very helpful. So first, because we only have 259 tasks, meta learning often operates over many more tasks. We're essentially going to try to augment our set of tasks. And we constructed 2 different kinds of tasks that are particularly well suited for code. One task is to classify the compilation error given a program. And another task is to essentially classify a particular token that has been masked out in multiple programs. One of the things that we found is if you mask out tokens at random, that doesn't work very well because predicting a variable name isn't very informative. So we specifically mask out kind of functional words in these programs, like for, or, in, or range, and so forth. So that allows us to create many more tasks. Another challenge that comes up is that if you only have around 10 or 20 examples, there's going to be some ambiguity for what the rubric item is corresponding to, especially if those examples make different mistakes. And so we can incorporate side information into the model to help reduce this ambiguity. And so, well, what side information do we have available? Well, we have the name of the rubric option, and we also have the text corresponding to the question. And this should provide a little bit more context to the model to allow it to understand what it's trying to classify on. And specifically, we'll take this side information, like the question text, encode that, and prepend it to kind of each of the layers in our transformer as the first token. Cool, and so this is going to reduce ambiguity. And then the last thing that we do is we don't just need to train on the Stanford data that we have. There's lots of Python data on the web. And so in practice, what we'll do is we took the CodeBERT model, which is a pre-trained model, pre-trained on code, and we'll initialize the embedding network from the pre-trained weights and then fine-tune the top M layers of the network. Cool. So those are the kind of the 3 main tricks. As a whole, we get an architecture that looks like this, where we have our student code sequence. We have multiple of those examples per class that we're going to embed and then form a prototype. We're going to condition this transformer on the question and rubric text and prepend those to each of the transformer layers in our model. And then some of these layers are going to be pre-trained with CodeBERT. And this will allow us to compute the prototypes. And then, of course, when we get a new test example, we'll also encode it through this model and compare it to the prototype, each of the 2 prototypes, to make a corresponding classification. Awesome. And so I already showed some of the deployment results. So offline results are maybe not quite as interesting as actually a live deployment, but we measured this on Hell.rubric and Hell.exams. And we compared this kind of architecture with all of the tricks that I mentioned. And we were able to get, on a Hell.rubric, we were able to get an average precision of 84.2, which is actually above human accuracy, which is pretty exciting. And you also might be somewhat surprised to find that humans aren't actually that accurate on this task, because it is actually pretty difficult to provide this feedback. It essentially corresponds to debugging students' code, and that can be time consuming, and if you're tired, you can make mistakes. And also, it's really important to kind of compare not just to a meta learning method, but also compare to kind of a supervised learning method to this approach. And we also find that the supervised learning baseline doesn't perform very well, and actually kind of treating this as a few-shot meta learning problem substantially improves over the performance. We also evaluated on the Hell.exam. And so this is actually a somewhat more realistic use case, because many times we will be applying this into an entirely new problem. And here we see that we still get pretty good performance and substantially better performance than a supervised baseline, but there is room to grow in comparison to a human TA here. And this kind of room to grow is part of the reason why we decided to fine tune the model on more data from the domain, rather than only using it as a kind of a 10-shot classification problem. And then in our analysis, we looked at actually the importance of the different tricks that I mentioned in different versions of the method. And so what this plot is showing is each of these dots is a different model. And we're looking at performance on Hell.rubric items and Hell.exams. And what we find is we basically ablated all of these sorts of aspects of the algorithm, including task augmentation, pre-processing, pre-training, the supervised baseline here, and also the best method shown in red. And I guess one of the things that's interesting about this ablation study is that almost all of these choices actually make a pretty significant difference in performance. And so, for example, if you look at task augmentation, if you take out and you no longer use that task augmentation, you see the performance drop from around kind of 73 to 74% down to around like 63 to 64%. So we see like a 10% degradation performance on a Hell.exam. Likewise, if we use kind of prototypical networks versus relation networks, we see a significant difference. And if we use like CodeBERT pre-training versus no pre-training, we again see a pretty big difference. And so in some ways, I think this is actually sort of a positive result for the meta learning community, because it means that kind of these differences in methods and these differences in pre-training methods and so forth are actually making a difference in this kind of application. And then the last analysis that we did is we looked at actually, we visualized the embeddings of the student solutions and we, for example, looked at the embeddings of all students, the embeddings of students on a particular question. And here the color is showing the numeric grade that the student received, and this sort of grade isn't passed as input to the model. And we kind of see these interesting clusters arise where kind of students with similar numeric grades are kind of being placed together. And this suggests that this may allow kind of future work to actually leverage these embeddings to maybe understand student misconceptions, group them together, and just generally get a better understanding of the classroom. Cool. So I guess the takeaway of the first part of the talk is that we saw that we can apply few-shot meta learning to this feedback problem in education and give feedback to students in both on kind of real data from Stanford, but also deployed in this live application in a setting where the students weren't otherwise going to be able to get feedback. Now, what I'd like to talk about for almost the rest of the talk is whether we can actually go further than this. And in particular, the feedback that we were giving on the first part of the talk was feedback on these short Python snippets. But a lot of kind of student work is more complex than that. So in particular, we're interested in whether we can give feedback on interactive student programs. And what I mean by that is that there's kind of a common computer science assignment isn't just to code up like a very simple program. Those very simple programs might appear in like intro classes. But as an example, in code.org, they have this assignment where the goal is to actually program a game. And in other scenarios, you might want to program a website. And this sort of software is very, it's useful. It's very motivating and engaging to the students. It can enrich the learning. And it's been found in a pretty large number of different classes. So these interactive assignments seem great, but they're also really difficult to provide feedback on. There is stochasticity in the programs, and also students may be creative with them, meaning that there's going to be an even larger space of possible student solutions. It's also really time consuming for humans to provide feedback on these assignments. It takes about 3 or more minutes to manually grade each student solution. And if you're code.org or any other massive course, and you have lots and lots of students, this means that this is going to result in an impractical amount of work to actually give feedback on these assignments. And that's exactly why these kinds of online courses don't provide feedback. And so our goal is to be able to try to automatically provide feedback so that we can reduce this enormous burden on grading and providing feedback, and also potentially allow the system to kind of iterate with the student. If you can have an automated feedback system, then the student can actually get instantaneous feedback rather than having to wait for a person to look at their work. So the problem setting will be somewhat similar to before, where we're going to have a rubric that corresponds to different misconceptions or different mistakes that the student could have made. And we'll have a data set of programs and rubrics. Now, one thing that's going to be different is actually in this work, we're only going to look at a single assignment. So there's only going to be one rubric. And what's going to be different is that essentially we're going to be treating different programs as different tasks rather than different rubrics as different tasks. We actually have a decent by education standards, decently sized data set, 3,500 labeled programs. This is maybe still somewhat small by machine learning standards, but it will actually allow us to be able to kind of better learn about the student mistakes. And then at test time, our goal is to be able to then look at a new student program and be able to give feedback on that new student program. So in some ways, you can maybe sort of treat this as a more standard supervised learning problem where we have kind of data points and labels, and then our goal is to generalize to a new data point. And output which bugs are in the program, essentially trying to predict the label in the rubric. Now, there's two different paradigms for automated feedback. So the first paradigm is what we talked about in the first part of the talk, where where we look at the program code directly and the model takes as input that code and makes predictions. This works well for the shorter programs that we saw before, but these methods struggle to scale if you have a very long program. And interactive programs are naturally much longer than the kinds of programs that we saw before. And so instead, what you can do, instead of actually looking at the code directly, you could actually have the system interact with the program behavior. And this kind of method is actually going to be independent of the length of the programming code, which is quite nice. It does assume that the program can compile and run, and so this is an important, this is one limitation of this approach. But because these interactive programs are longer, we're going to opt for the second approach in this part of the talk. So the way that it'll work is the agent is going to interact with the program, and so is actually going to, like, in this case, move this paddle at the bottom of the screen and interact with the program to learn about the behavior of the program and try to find bugs. And so, for example, if it sees that it bounces off the goal and doesn't actually increment the score, this means that it should provide feedback on this bug in the program. Unfortunately, existing work to this problem would just essentially give feedback by providing coarse binary feedback to say that the program is incorrect. And what we'd like to be able to do is to actually give much more fine-grained feedback to the system to say that the ball is incorrectly bouncing off the goal. And so this is the more detailed rubric-based approach can actually accomplish this if you can classify the correct, classify the rubric option items correctly. Now, what does this exactly entail? So in this case, unlike just looking at code, you actually have to explore. You have to take actions in the environment. And you need to do this in a targeted way to try to seek out where possible bugs in the program might be. And you also need to adapt your exploration behavior depending on the program. So some programs may generate lots of different balls, and you need to be able to adapt your behavior to those differences in different programs. And so the approach that we're going to take is we are going to essentially learn how to explore these programs. We're essentially going to take a meta reinforcement learning approach where we learn an exploration policy that allows us to correctly adapt to the different student programs. And so this involves first learning an exploration policy pi that takes us in a program and produces a trajectory in that program or a set of trajectories in that program. So for example, if we want to, what this looks like is kind of an example like this, where it actually maybe tries to hit the ball, sees if it will hit off the wall and so forth. And then with this exploration policy, with these trajectories, we can then train a classifier that takes as input these trajectories and predicts the corresponding rubric label. And so this will predict the errors that the program has. So there's these two aspects of the problem. And we can train the exploration policy and the feedback classifier essentially with respect to trying to maximize the likelihood of predicting the correct rubric label. And so this corresponds to this objective right here. This might look a little bit complicated, but essentially what this corresponds to is sampling a program and rolling out the exploration policy to produce a trajectory, and then maximizing the probability of the correct label. So this is fairly simple, and especially training the feedback classifier is fairly straightforward. Once you have the trajectories from the exploration policy, you can just train it with standard maximum likelihood or using a cross entropy loss. Now, what's challenging is how to actually figure out how we should train this exploration policy in a way that learns how to explore a new program and adaptively explores different programs based on what it sees. So this exploration policy is going to be a recurrent neural network. And a naive way to train this exploration policy would be to just simply train it to basically essentially treat the output of the feedback classifier as the reward at the end of the episode. And this should in principle train it to lead to behaviors that allow the feedback classifier to make accurate predictions. But this was going to, in practice, actually lead to a very sparse reward. So as an example, say that the exploration policy is kind of interacting with the program. It moves over to the left to hit the ball. It then hits the ball towards the goal and then sees the score doesn't increment and then continues exploring and eventually, in this case, explores and sees that that the ball doesn't hit the ball in this case. And then maybe that's the end of the episodes that the exploration policy collects. Now, if you use the naive approach of basically rewarding it at the end of the exploration episodes, what will happen is that we'll get a reward at the floor right here after it's explored fully throughout these episodes. However, the bug here was actually discovered here. This is where we saw that it hit the goal and the score didn't increase. And so it'd be nice if we could actually reward it here rather than rewarding it at the very end of the episode to give it a more shaped signal. And this is where we'll actually use a meta reinforcement learning algorithm, specifically the DREAM algorithm, to try to provide credit at 3. I'm not going to go into all the details of how DREAM works, but really the key intuition here is that we can change the reward. Instead of giving it a sparse reward at the end, we can use the reward to maximize the information gain. And so you can use your classifier and give it a reward based on how accurate is it at the current time step versus the next time step. And if it's more accurate at the next time step than the current time step, then you should get a higher reward. So this is basically the increase in information that the current time step gives you about your accurate prediction. Okay, so that's the gist of the approach, where we're going to be essentially training this exploration policy to explore these different programs and adapt to different student solutions, depending on the ball speed, depending on kind of different aspects of the program in order to seek out the different bugs. And then once we have the exploration policy, we'll also jointly train this classifier, and the classifier will actually fill in the rubric to actually give the students the feedback in the end. Now, in our experiments, we wanted to get a sense for two questions. First, how feasible is this problem of generating automatic feedback with this approach? And second, can this approach also handle the fact that students might be creative and give generate different kinds of programs? In all of our experiments, we'll use this bounce programming assignment that I had as an example throughout the talk. And this assignment is actually from code.org. It's a data set. There's a data set of real student submissions, 700,000 real student submissions that was released by this prior work. And we are training the system on 3,500 of the programs. So actually a very small subset of this full data set, and then we're holding out the rest. And then in terms of evaluating how feasible generation is, we're going to compare to a few different things. We're going to compare to human graders. We will compare to the naive approach of directly maximizing the reward at the end of the episode. And we'll also compare to this existing state-of-the-art approach that actually is only designed for giving course feedback, although we can kind of roughly kind of adapt it to the setting of trying to provide more fine-grained feedback. In our experiments, we evaluated both accuracy and F1, and we found first that humans are quite accurate at this task. So they're, in this case, kind of above 90%, both in terms of accuracy and in terms of F1 score. But of course, it's infeasible for humans to grade the data set. It would require 4 or more years. In contrast, the approach that I mentioned, it's a lot faster. And it's also actually within 1.5% of human accuracy. So it's essentially providing feedback that's comparable to the quality of human feedback and is able to do so much more quickly. Now, if we look at these prior approaches, the naive approach of assigning credit at the end of the episode doesn't perform well at all, especially in terms of F1 score. And this shows that appropriately assigning credit is really critical for learning how to explore. And lastly, if we compare to kind of the state-of-the-art approach that I mentioned before, we're able to improve on this approach by around 18.8%. So overall, this suggests that we're able to do quite well on providing feedback on these assignments. Here are some kind of qualitative examples of what the behavior looks like. So we see that the exploration policy will figure out, we'll try to explore to try to have the ball hit the goal. It will try to explore so that the ball purposefully hits the floor. So this is not a typical behavior you might see from a reinforcement learning agent. It also tries to see what happens if the ball hits the wall. Now I should mention that this sort of case, in this case, it is actually able to kind of get a clear signal for whether the ball hits the wall. But this case where there's lots of different balls coming up is actually exactly the case where we see the gap between the performance of this method and human performance. And in particular, when you have lots of different balls, if one of the balls kind of misses the paddle at the same time as another ball is hitting the goal, then it's hard to figure out which ball is causing the score to change. And that makes it difficult to kind of discern what the underlying bug in the program is. So this is kind of where the kind of remaining like 1.5% gap lies. Okay, and then the second question that I mentioned is whether we can handle some degree of student creativity. And one type of student creativity that we noticed in the data set is differences in ball speed and differences in paddle speed. So not all students kind of program the ball and the paddle to move at exactly the same speed. And we wanted to see whether the system can handle student creativity by evaluating on held out ball speeds and held out paddle speeds. And we measured kind of the typical metrics that I mentioned before. And kind of roughly what we can see is if we compare to having both the ball speed and the paddle speed being held out compared to neither of them being held out, we roughly see the performance is pretty similar for these two scenarios. And that suggests that we are able to kind of handle this form of student creativity on the assignments. Cool. So I guess to summarize, the in the first part of the talk, I talked about applying feedback to these code snippets, and then I just showed how we can apply ideas from meta reinforcement learning to learn how to explore and be able to adapt to different student programs in a way that allows us to provide feedback on these more challenging interactive assignments. And I'd like to finish by talking about what we learned in this process of applying meta learning to these real world problems and what are some of the outstanding challenges. Before I talk about the final challenges, I think I'll mention, it'd be good to mention that to our knowledge, this is kind of one of the first successful deployments of machine learning driven feedback in open-ended student work. So it's providing a win for education. And in my mind, it was also very satisfying from a meta learning standpoint because it provides and introduces this kind of pretty interesting real world application for few-shot meta learning and meta reinforcement learning. Now, some of the things that we found that were hard and difficult. So first is that in education, there's limited meta training data. You don't have that much data of student work that is labeled with the correct rubric items. We found that task augmentation can be helpful here. There's also some other works that have developed methods for task augmentation. It seems also possible that regularization might help as well. And so these kinds of methods, I think, are along the lines of trying to improve this meta learning methods when we have limited meta training data. But I think that more work is needed here to provide fairly kind of general purpose approaches for this. A second challenge that I swept under the rug for the most part is that not in the second work, but in the first work where we have student solutions, it's not actually clear where the support set should come from, where those labeled training examples that we adapt with come from. You can randomly sample examples, but when you randomly sample examples from your data set is naturally imbalanced. Usually more students get the answer right than get the answer wrong. And so if you randomly sample, you might actually get a very imbalanced support set, possibly that only has correct answers. And that actually isn't going to give you a very informative support set that allows you to learn how to classify the different rubric items. And so I think that there's a lot of room for future work that doesn't require a support set that maybe allows the system to use active learning to actually kind of query out the support examples, or maybe approaches that allow experts to more effectively interface with the data and design support sets. Another challenge that comes up is if our model isn't perfect, it would be great if the model can be confident about some examples that it is accurate on and defer harder examples for the instructor. This is a very natural setting for essentially selective classification. And if we had more calibrated models, then we would be able to still have a substantial impact in these applications without having to achieve perfect accuracy. And then one of the last challenges that we ran into is that specifically in the code in place deployment, we saw that there was some sort of distribution shift between the Stanford meta training data and the code in place deployment data. We don't have a great sense for what the distribution shift was. We found that fine tuning was helpful, but I think that we need more tools to try to diagnose this kind of distribution shift between meta training and deployment, and also to ultimately mitigate and improve the robustness of these models. And there's also a lot of work on this in the machine learning community. As one example, Pangwei and Shiori worked on this WILDS benchmark that tries to illustrate some of the challenges of distribution shift. I think that there's a lot of work to be done here, not just in machine learning, but also in the meta learning field as well. And then lastly, some future directions. We were focusing on programming courses, on intro computer science courses here, but you could imagine that we could apply these same sorts of ideas beyond programming. And very little in the methods that I presented is actually specific to code. And so many of these ideas should be able to translate to more broad kinds of courses. There's also risks of moving beyond programming, and there might be challenges of bias and subjectiveness in these courses. And so it's important to be aware of those risks when working on these problems, and consider human in the loop reinforced machine learning and other aspects to try to address those challenges. We use it in code in place. We could also consider using it in university courses. We would need a really clear value add to the students, not just to the instructors for this sort of case. And this is something that I think that this is something that I think is on the horizon and something that could happen in the near future, given given how well these methods seem to work. And then lastly, I think it's great for not just, I don't think we should be the only people working on this problem. I think it'd be great if everyone in the research community was able to work on this kind of problem. The code.org programs that we worked with in the second work are publicly available, making it possible for people in the community to work on it. But unfortunately, the data set in the first part of the talk is not publicly available. And there's a lot of challenges that need to be overcome for broader data releases, specifically around student privacy and kind of ethical considerations. It's also possible that private or federated machine learning might provide a possible alternative to releasing the data set in full. Yeah, so with that, I'll leave kind of a few takeaways. First, I think educational feedback is a pretty exciting real-world few-shot learning problem. We saw that meta-learning and meta-RL both provide substantial value, and there's also lots of challenging open problems. I really like to thank and acknowledge all of my collaborators, especially Mike, Evan, and Moritz, who led the work that I presented. And if you're interested in learning more about meta-learning, I teach a course on meta-learning at Stanford, and all the lecture videos are available online. Happy to take some questions.
So thank you very much for the lovely talk. And do we have any questions on the floor?
Thanks, Chelsea. Great talk. So part of the process here is to have the TAs create like 1,000 tasks, right, or exams. Is there a scope here, you think, to scale this up further for weak supervision? So you could get more data, maybe make the meta-learning work better, and maybe even be more robust against errors in those TA examples.
Yeah, so a couple notes here. I should mention that in the first work, in our offline results, we were only using 20 labeled examples. And so that's something that's quite small. In the deployment, we were using 1,000 examples in part because of the domain shift. We needed to fine tune the model a little bit. And I think that there should be ways to certainly scale that as well. I think that weak supervision is interesting. In some ways, the task augmentation that we're doing is a form of weak supervision as well. I also think that there's in some ways, in terms of getting more meta training data, I also think that there is actually lots of data out there. It's just a challenge of releasing it because of student privacy and everything. And so it seems like it should be possible in the future to get more data around this. Yeah, I guess specifically for weak supervision, we haven't thought about it too much, although I could certainly imagine active learning to try to provide more informative examples, or yeah, it seems possible that kind of weak other forms of labels beyond the rubrics could also be quite informative and help address kind of the data challenges as well.
Any other questions?
Thanks, Chelsea, for the really nice talk. I have one question. You mentioned the risks of biases and subjectiveness. And well, you showed that in your solutions there, that problem didn't occur, and that's great. But I'm wondering, going forward, in cases where it might occur, can you also think of using meta-learning or AutoML or any type of automated solutions in order to avoid these biases in an automated manner? So for example, constraints, multi-objective optimization, etc.
Yeah, I think that's an interesting question. So I guess first I'll mention that in our work, we stripped all of the comments out of the code. And so the code contains very little information about the student. And so we weren't able to see any biases in what we were seeing, although if you applied this, for example, to open-ended text or something with handwriting, I could imagine biases creeping in at that point. In terms of using meta-learning for addressing fairness and biases, I I think I feel like I'm actually not that optimistic. I think that I think in some sense we don't actually have good metrics for fairness, and there are actually works that show that that you can have multiple seemingly sensible definitions of fairness that actually are conflict with each other. You can't have both of them. And so I think that if we want these methods to help improve fairness and address biases, I think we need to have good metrics for it, because ultimately we are defining a good metric and optimizing it. That said, I will mention that there is some nice work by a student in Regina Barzolet's group at MIT that used meta-learning at bi-level optimization to basically find trained test splits that were challenging in the data set for a model. It basically had an inner loop learner that was learning a task and an outer loop learner that was defining the trained test split in a way that was kind of adversarial. And they found that they were able to uncover some biases in data sets from that, like spurious correlations and so forth. And so I think that approaches like that do give me some optimism for at least having a diagnostic tool for understanding the bias, not necessarily having a tool for completely like improving bias, but it's something that I think is a step in the right direction.
Any other questions? No? Do you have another?
Yeah, another question I would have is, so you use prototypical networks. Is that, so that was probably for the scale of the problem, or like how would you rate these days prototypical networks versus the MAML-like approaches? Could those also be applied here, or what are your thoughts on that?
Yeah, that's a great question. So prototypical networks was actually the first thing that we tried. And again, we were not expecting things to work as well as they did at the outset. And I think that prototypical networks is particularly well suited for this problem because it is a pretty large scale problem. Prototypical networks are very lightweight, and they're also very well suited for classification problems. And so that makes them, I think, a good choice. I suspect that you could also apply an optimization-based method like MAML to the problem as well. And I think that it could work well. It possibly could even allow you to do better in scenarios where you have some distribution shift, like in the deployment, because it makes it very easy to fine-tune the model and actually optimizes for fast fine-tuning. So I think in scenarios like that, it may work well. So yeah, we mostly use it for its simplicity and so forth. I think that in scenarios, if it was a regression problem, then we wouldn't be able to use prototypical networks, and we would probably use an approach like MAML. And yeah, those are some of our thoughts. I'll also say in the meta-RL setting, we are using kind of a black box approach where we just have this RNN that learns about the program and adapts its exploration strategy. And so we're actually seeing kind of a few different kinds of methods represented here.
Okay, we also have a question online, which is about the protoformer actually. So the question is, how do you define the item to skill or task mapping? Is it from instructors, or maybe you could clarify a bit more there?
Yeah, so the instructors are defining a rubric for each example that has different rubric options. Each of those are binary classification tasks. And once we have that rubric, we can define the tasks automatically by treating each of those options as a task. And so it's actually quite simple. And yeah, basically every different option is a task, and that we use that to construct our meta training data set. And then at test time, when we're given a rubric, we actually adapt to each of those tasks, each of the options to and get prototypes for each of those options separately, completely independently, to fill in the rubrics.
Another one, yeah.
Well, Frank has two questions. I really want to try this in my own courses. What's stopping me a bit here is that the rubrics, which are much harder in my case to use, for instance, and I think in many other cases, rubrics are not easily doable. Is there, so one question would be like, how fixed is this approach to rubrics? can we get rid of rubrics? And for instance, one idea might be more like continual learning, where you have a TA that discovers an error. That's then a new class of error that you have. And then other TAs maybe find new errors. And then in a continual way, you may be able to learn. Is that maybe doable? Would that work?
Yeah, I think that's a really interesting question. And in some ways, it also relates to my point about how like we want to get rid of support sets as well. You kind of want to discover, like, given an unlabeled data set, can you define both the rubric and grade everything jointly? We haven't explored that ourselves, but I think that there certainly seems like a possibility for doing that. I also, like, in the meta learning literature, I think there's work on trying to do kind of open class or open set classification, where you have some like kind of unknown classes as well. You may also become a little bit more of a kind of a meta clustering problem as well. So yeah, I certainly think that there's possibilities there. The specifics of these approaches do assume rubrics. And so you certainly can't apply these out of the box without a rubric, but I certainly think that problem is pretty interesting, and the meta training data will still have rubrics. And so you may also be able to learn about the rubrics from the meta training data and use that to, rather than just having it be a fully kind of unsupervised clustering problem or kind of meta clustering problem. I think that, I think that there's a lot of possibilities there. It's it would also be pretty exciting.
In the spirit of open rubrics and trying to get rid of them or maybe learning them, maybe one question from my side: could we learn them implicitly in a manner where, instead of removing the biases for the student, could we potentially promote certain forms of creativity in students in these evaluation tasks, so we do know how experts solve the problem and we could sort of bootstrap off of them in a way? Yeah,
absolutely. I guess first I should mention that I do think that, at least in the examples that we showed, the rubrics are not that hard to define, at least in these courses, but there are definitely examples where they are much harder. Precisely in examples where you want to kind of promote creativity and so forth. This is something that Chris and I have talked about a fair amount. Chris Peach is very passionate about improving the experience for students and promoting things like creativity and so forth, because that really improves the student experience. I think the problem is very hard, because even defining what creativity is very difficult. We saw some examples of being able to adapt to different elements of human creativity. And I think that you could imagine like using the embeddings, like the prototypes, possibly to try to encourage some amount of creativity, to try to, for example, like encourage students to be different from the other embeddings, for example. But still, I think it's a really hard open problem, and something that I'd love to see future work address.
Well, thank you so much. So with that, I guess we'll end the session. Thank you very much again, Chelsea, for your time and the presentation.
Yeah, thank you for inviting me.